Okay, let's begin our discussion on recurrent and transient states in random sequences.
We'll start by considering a random sequence which we'll denote as x that maps from omega to script x raised to the power of z plus. This sequence begins with an initial state, let's say x not equals x, where x is an element of script x. We are also interested in the kth hitting times to a specific state, let's call it y. For all k in the set of natural numbers, we denote this kth hitting time as tau k, which is equivalent to tau x superscript set containing y comma k. This is defined inductively. Tau k is the infimum of the set of all n greater than tau k minus 1 such that xn equals y, and we define tau not to be 0. Next, we define a sequence called the inter-return time sequence denoted by h, which maps from omega to n raised to the power of n. For any k in the set of natural numbers, hk is defined as hx superscript set y comma k, which is simply tau k minus 1. Now let's formalize a couple of important probabilities. For a random sequence x mapping from omega to script x raised to z plus with an initial state xn ot equal to x, first, the probability of eventually hitting state y is denoted by f sub xy, which is defined as the probability given the process starts at xp sub x that tau u1 is less than infinity. Second, the probability of the first visit to state y occurring specifically at time n, where n is a natural number, is denoted by f sub xi superscript n. This is the probability starting from xp sub x that tau 1 is exactly equal to n. It's worth reminding ourselves that the event tau 1 is less than infinity, meaning the hitting time is finite, can be expressed as a disjoint union of events. Specifically, it's the union over all natural numbers n of the event tau 1 equals n. Therefore, it follows directly that f sub xy, the probability of eventually hitting state y, is the sum over all natural numbers n of f sub xy superscript n. If f sub xy, which is the probability starting from xp sub x, that tau u1 is less than infinity, equals 1 for all possible initial states, x in script x, then tau u1 is almost surely finite. Consequently, tau u1 is a stopping time. Let's define two important distributions. Starting from an initial state x, first, the distribution for the first hitting time to state y is called the first passage time distribution. This is denoted by the pair, the sequence f sub xy superscript n for n in natural numbers and 1 minus f sub k. Second, the distribution for the first return time to the initial state x itself is called the first recurrence time distribution. This is denoted by the pair, the sequence f sub x superscript n for n in natural numbers and 1 minus f sub x. Now we can define what we mean by recurrent and transient states. A state y in script x is called recurrent if f sub yy equals 1. Conversely, a state y is called transient if f sub yy is strictly less than 1. For any state I in script x, we also define the mean recurrence time. This is denoted by mu sub yy and is defined as the expectation when starting in state E expectation sub y of tau 1. Keep in mind that for any transient state, the mean recurrence time is infinite. For any recurrent state, y in script x, we can write tau 1 as tau 1 times the indicator function of the event. The tau 1 is less than infinity. This can be expanded as the sum over all natural numbers n of n times the indicator function of the event, that tau 1 equals n, and this holds almost surely. Therefore, the mean recurrence time mu sub y is given by the sum over all natural numbers n of n times f superscript n sub y. Building on this, for a recurrent state y in script x, if its mean recurrence time mu sub y is finite, then state E is called positive recurrent. On the other hand, if the mean recurrence time is infinite, then state y is called null recurrent. We have a proposition for a homogeneous discrete Markov chain X, which maps from omega to script x raised to z plus. The probability starting from state x p sub x that the number of visits to state y n sub y of infinity equals k is given by a piecewise function. It's 1 minus f sub xy if k equals 0, and it's f sub xy times f sub y raised to the power k minus 1 times 1 minus f sub y if k is a natural number. Let's look at the proof for this proposition. We can express the event of having 0 visits to state y, which is n sub y of infinity equals 0, as the event tau 1 equals infinity. Furthermore, for any natural number k, the event of having exactly k visits to state y, n sub y of infinity equals k, can be written as the intersection of tau k is less than infinity and tau k plus 1 equals infinity. This is equivalent to the intersection from j equals 1 to k of the event hj is less than infinity intersected with the event hk plus 1 equals infinity. Recall that h mapping from omega to n raised to n is an independent random sequence where the subsequence k for k greater than or equal to 2 is identically distributed. Also, the probability starting from xp sub x that hj equals n is the same as the probability starting from yp sub y that tiu 1 equals n for all j greater than or equal to 2. Therefore, we get that the probability starting from xp sub x of n sub y of infinity equaling k is p sub x of h1 less than infinity times the product from j equals 2 to k of p sub x of hj less than infinity times p sub x of hk plus 1 equals infinity. This simplifies to f sub xy times f sub y raised to k minus 1 times 1 minus f sub y. As a corollary to this, for a homogeneous Markov chain X, we have that the probability starting from xp sub x that n sub y of infinity is less than infinity is equal to the indicator function of f sub y being less than 1 plus 1 minus f sub xy times the indicator function of f sub y being equal to 1. The proof follows by writing the event n sub y of infinity is less than infinity as a disjoint union of the events n sub y of infinity equals k for all possible k, which then yields the result. Another important reminder, for a time homogeneous Markov chain X mapping from omega to script X raised to Z plus, we have two key results. First, the probability starting from xp sub x, that n sub y of infinity equals infinity, is f sub xy times the indicator function of sub y being equal to 1. Second, the probability starting from yp sub y, that n sub y of infinity equals infinity, is simply the indicator function of f sub y being equal to 1. A further corollary states that the mean number of visits to state y starting from a state x, which is expectation sub x of n sub y of infinity, is given by f sub xy divided by 1 minus f sub y times the indicator function of f sub y being less than 1 plus infinity times the indicator function of f sub xy being greater than 0 and f sub y being equal to 1. As a reminder, for any state y in script x, the expectation starting from y, expectation sub y of n sub y of infinity, f sub yi divided by 1 minus f sub y times the indicator function of f sub y being less than 1 plus infinity times the indicator function of f sub y being equal to 1. That is the mean number of visits to an initial state. Y is finite if and only if the state I is transient. In particular, this corollary implies several important consequences. First, a transient state is visited a finite number of times, almost surely. This follows directly from our earlier corollary, since the probability starting from xp sub x of n sub y of infinity being less than infinity is 1 for all transient states y in script x and any initial state x in script x.
Second, a recurrent state is visited infinitely often, almost surely. This also follows from the earlier corollary, because the probability starting from yp sub y of n sub y of infinity being less than infinity, 0 for all recurrent states y in script x. And third, in a finite state Markov chain, not all states can be transient. Let's prove this last point. To see this, we assume, for the sake of contradiction, that for a finite state space script x, all states in script x are transient. If all states are transient, then we know that n sub y of infinity, the total number of visits to state y, is finite almost surely for all states y in script x. It then follows that for any initial state x in script x, the probability starting from xp sub x, that the sum over all y in script x of n sub y of infinite can be bounded. This probability is p sub x of the union over y in script x of the event n sub y of infinity equals infinity. By Boole's inequality, this is less than or equal to the sum over y in script x of p sub x of n sub y of infinity equals infinity. Since all states are transient, this sum is 0. Thus, it follows that the sum over y in script x of n sub y of infinity is also finite almost surely for all states y in script x. Given that script x is a finite state space, however, we know that the sum over y in script x of n sub y of infinity is actually the sum over k in natural numbers of the sum over y in script x of the indicator function that xk equals y. This sum must be infinite as the process must be in some state at each time step. This leads to a contradiction, proving that in a finite state Markov chain, not all states can be transient. We have another proposition for a homogeneous discrete time, Markov chain DTMC X mapping from omega to script x raised to z plus a state y in script x is recurrent if and only if the sum over k in natural numbers of p sub y superscript k is infinite. It is transient if and only if this sum is finite. The proof recalls that if the mean recurrence time to a state y in script x, which is expectation sub y of n sub y of infinity and equals the sum over k in natural numbers of p sub y superscript k is finite, then the state is transient. If this sum is infinite, the state is recurrent. A corollary follows for a transient state y in script x. The limit as n approaches infinity of p sub xy superscript n is 0, and the limit as n approaches infinity of the sum from k equals 1 to n of p sub xy superscript k all divided by n is also 0. For the proof, if y is a transient state in script x and x is any state in script x, we know that expectation sub x of n sub y of infinity, which equals the sum over n in natural numbers of p sub xy superscript n, is less than infinity. Since this series sum is finite, it implies that the terms in the sequence must go to 0. So the limit as n approaches infinity of p sub xy superscript n is 0. Furthermore, we can write that the sum from k equals 1 to n of p sub xy superscript k is less than or equal to expectation sub x of n sub y of infinity, which in turn is less than or equal to some finite m for some natural number m. Therefore, the limit as n approaches infinity of the sum from k equals 1 to n of p sub xy superscript k divided by n must be 0. Let's consider a lemma regarding stopping time. For any state y in script x, let h mapping from omega to n raised to n be the sequence of almost surely finite intervisit times to state y. Let n sub y of n, which is the sum from k, equals 1 to n of the indicator that xk equals y be the number of visits to state y in the first n time steps. Then n sub y of n plus 1 is a finite mean stopping time with respect to the sequence h. For the proof, we first observe that n sub y of n plus 1 is less than or equal to n plus 1, and hence it has a finite mean for each natural number n. Further, we observe that the event n sub y of
n plus 1 equals k can be completely determined by observing h1, h2 up to hk. This is because the event n sub y of n plus 1 equals k is equivalent to the event that the sum from j equals 1 to k minus 1 of hj is less than or equal to n, which in turn is strictly less than the sum from j equals 1 to k of hj. This event belongs to the sigma algebra generated by h1 through hk. Now we arrive at an important theorem. Let x and y be states in script x such that f sub xy equals 1, meaning state y is accessible from state x and state y is recurrent. Then the limit as n approaches infinity of the sum from k equals 1 to n of p sub xy superscript k all divided by n is equal to 1 over mu sub y, the reciprocal of the mean recurrence time of state y. Let's outline the proof. Assume y in script x is recurrent. The proof will have three main parts. In the first two parts, we will demonstrate that if we start from state y, the limiting empirical average of the mean number of visits to state y, that is the limit as n approaches infinity of 1 over n times expectation sub y of n sub y of n equals 1 over mu sub yy. In the third part, we will show that for any starting state x in script x such that f sub xy equals 1, the limiting empirical average of the mean number of visits to state y, which is the limit as n approaches infinity of 1 over n times expectation sub x of n sub y of n is also equal to 1 over mu sub yy. For the lower bound, we observe from lemma 2.1 that n sub y of n plus 1 is a stopping time with respect to the intervisit times h. Furthermore, the sum from j equals 1 to n sub y of n plus 1 of hj is strictly greater than n. Applying Walt's lemma to this random sum, we get that the expectation starting from y expectation sub y of n sub y of n plus 1 times mu sub yy is greater than n. Taking limits, we obtain that the limit inferior as n approaches infinity of the sum from k equals 1 to n of p sub y superscript k divided by n is greater than or equal to 1 over mu sub yy. Now for the upper bound, let's assume the process starts at state y, so xnot equals y. Consider a fixed positive integer m. We know h is an IID sequence. We then define truncated recurrence times. Let's call them h bar, mapping from omega to the set of integers from 1 to m raised to the power of n. For all j in natural numbers, h bar sub j is defined as m and hj, which means it's the minimum of m and hj. It follows that this new sequence h bar is also IID, and importantly, h bar sub j is less than or equal to hj for all natural numbers j. We define the mean of these truncated recurrence times as mu bar sub yy, which is the expectation starting from y expectation sub y of h bar 1. Due to the monotonicity of truncation, we have that mu bar sub y is less than or equal to mu sub yy. Next, we define a random variable tau bar sub k as the sum from j equals 1 to k of h bar sub j for all natural numbers k. It's clear that tau bar sub k is less than or equal to tau k for all k. We can then define an associated counting process that counts the number of these truncated recurrences within the first n steps. Let's call this n bar sub y of n, defined as the sum over k in natural numbers of the indicator function that tau bar sub k is less than or equal to n for all natural numbers n. We can conclude that n bar sub y of n plus 1 is a stopping time with respect to the IID process h bar. Also, sample pathwise n bar sub y of n is greater than or equal to n sub y of n. Furthermore, we have that the sum from j equals 1 to n bar sub y of n plus 1 of h bar sub j, which is tau bar sub n bar sub y of n plus 1, can be written as tau bar sub n bar sub y of n plus h bar sub n bar sub y of n plus 1. This entire sum is less than or equal to n plus m. Continuing with the upper bound, applying Walt's lemma to the stopping time n sub y of n plus 1 with respect to the IID sequence h and to the stopping time n bar sub y of n plus 1 with respect to the IID sequence h bar, and using the monotonicity of expectation, we arrive at the inequality expectation sub y of n sub y of n plus 1 times mu bar sub yy is less than or equal to expectation sub I of n bar sub I of n plus 1 times mu bar sub yy, which in turn is less than or equal to n plus m. Taking limits, we obtain that the limit superior as n goes to infinity of the sum from k equals 1 to n of p sub yy superscript k divided by n is less than or equal to 1 over mu bar sub yy. By letting m grow arbitrarily large, mu bar sub ae approaches mu sub a way, and we obtain the desired upper bound. Finally, let's consider starting from an arbitrary state x. We observe that p sub xy superscript k can be expressed as the sum from s equals 0 to k minus 1 of f sub xy superscript k minus s times p sub y superscript s. Since we are given that f sub xy equals 1, which means the sum over k in natural numbers of f sub xy superscript k equals